So, welcome back student to the complex analysis course. In the last class we started something interesting called residue. If a function fz is expanded in terms of Euler series, there will be many terms associated with that. So, like this, a minus k divided by z minus z0 k, a minus k plus 1 z minus z0 k minus 1 and so on, and one term we will get which will be the last term of the principal part, which is something like this. Up to this is the principal part because this z minus z0 is in the denominator, and then we will have some terms like this. So, we are looking for this particular term a minus 1, which we call the residue. This term is of our interest. Now, there are a few recipes we used last day. So, let me once again write these recipes. So, first is if the function has a simple pole, then we normally write this residue in this form. Say z0, I want to find the residue. So, it is something like limit z tends to z0, z minus z0 function multiplied by the function. So, this is the one form, and second form was something like this. If the function do not have a pole of order 1, singularity of pole, simple pole, rather it has pole of order n or pole of order k, then it will be something like 1 divided by k minus 1 factorial dk minus 1 dz k minus 1 z minus z0 to the power k function of z. It was something like this, and we use both the, we exploit this both the cases and find some problem. So, today we will do, let me erase this. Today we will like to learn another way to calculate this residue. Say some function of z is given as g of z h of z. In some special case, I can exploit this whatever the thing I will going to derive. The special case is 1 gz and hz, these two functions. Fz is a function which can be represented as the ratio of two functions, and gz and hz both are analytic. Second thing is that the singularity, if the singularity at is 0, so z0, say z0 is a singular point, say z0 is a singular point, then the g z0 should not be 0 and h z0 should be equal to 0, and this 0 will be of order 1. That means we should have a simple pole at z equal to 0 for h. So that the function is not analytic at z equal to 0, it is obvious. So we have two conditions in our hand. If these two conditions satisfied, then we can derive something from this. Then let me first write the result. Then residue of this given function at z0 point should be equal to g of z0 divided by h prime of z0, where h prime is a derivative. H prime is a derivative of h function. So, h prime z0 is the derivative of h function, which is a function of z with respect to z at z equal to z0 point. So, this is the recipe. So, this recipe is useful, we will see that. Last day I just show one example. So, today we will exploit more examples and try to find out how these things will be applicable. But before that we need to show that this is the correct thing. So, how to prove that? How to prove that? Okay. So, in order to prove, so let me first define how h prime z is given. It is limit z tends to z0 h of z minus h of z0 divided by z minus z0. So, this is the limit. So, let me erase this, it is not of any. So, let me erase this part also, so that I can have the place to write something. So, this is the derivative I can write in this form. So, now in the condition we mention one thing, I just erase that h of z0 is equal to 0, that is the one condition that we have. So, here we have something h of z0. So, this quantity is going to vanish. So, eventually this quantity is limit z tends to z0 h of z divided by z minus z0. This quantity I have. So, this is the quantity I have. Now, from the concept of the recipe, so now I am going to use whatever the recipe we have, standard recipe, that residue of function at z0 is nothing but limit z tends to z0. The same thing I am writing once again, which I have just erased few minutes ago. This is the blindly, if I use the formula, then this will be the formula for finding the residue. Now, I have something extra in my hand and fz is given in some form. So, let me write down the fz. So, z minus z0 and my fz is the ratio of these two functions. So, I will going to write that. So, gz by this. Now, if you look carefully, then you will find that this quantity is already here. This quantity is already here with the limit z tends to z0, h prime z is already there. So, if I replace this divided by this from here, then it will come like limit z tends to z0 g of these things divided by h prime of z. I replace this entire thing from here. So, h prime is given by this. So, I just replace this quantity here to this. So, I will have something. Now, I am allowed to put the limit. If I put the limit, it will come like g of z0 divided by h prime of z0, which is our recipe and which is already written here. So, this is the same thing that I have written here, and I just prove that this is one another way you can consider to find out the residue, and it is an interesting way to find out the residue provided this condition are satisfied. For example, z of z0 should not be 0 and h of z0 should be 0, otherwise it will not going to be applied. Okay, after having this form, let us try to use this in some practical problems, and that will be useful. So, let us try to find out few problems where we can use this. So, last day we have some problem in our hand. So, let me remind the problem. So, the problem was something, problem 1 say, or example 1, whatever. Fz was given as 1 divided by sine of pi z. This is the function that is given to us. Now, you can readily understand that the singularity, there are many singularities associated with these functions. For example, for all z, say z equal to 0 will be singularity, and all integers of z is a singular point. So, z equal to plus minus 1 singular point, z equal to plus minus 2 and so on. So, if I, this is my x axis and this is my y axis, this is a jet plane. In the jet plane I have a singular point here for this function. If this is 1, I have a here, I have some singular point here, 2, it is 3, I have here, and so on. Here also I have minus 1 here, I have minus 2 here, and so on. So, we have many discrete singularities here, and if I want to find out what is the singularity at z equal to 0 point for the time being, then let us find. So, the function, if you look it looks like g of z divided by h of z, right, because g of z is 1, h of z is this sine pi z, and the condition suggests that when the singularity is as, say, singularity I am taking just one point, singularity at z is equal to 0. So, if the singularity is z equal to 0, then g of 0 obviously not equal to 0, it is just equal to 1 because the function is constant. What about this h of 0 is 0. So, these two conditions is satisfied, both the things are analytic in sense, there is no problem with the analyticity. Even at z equal to 0 point, sin z will be analytic because at z equal to 0 point this function vanishes. So, there is no problem in the analyticity. So, then I readily can say the residue of this function, given function at 0 point, according to our recipe, it should be g of 0 divided by h prime of 0, because that is the recipe I just derived, that at the singularity whatever the function of z, at the singularity whatever the derivative of the function h function at that point. So, g of 0 here is 1, no problem with that. H function I know, h function is sin pi z. So, if I make a derivative of this function with respect to say z, I will have pi cos of pi z. It should be evaluated at z equal to 0 point. So, when I evaluate at z equal to 0 point, the result that is in my hand is 1 divided by pi. So, that means the residue of this particular function seems to be 1 divided by pi. Now, if I do the same thing for z equal to 1 point, then the result will be something different. So, let me do that also. Let me do that also, because I am trying to find out the residue at that particular point, but here also we have some problems. So, here also I have some points where we should have some kind of singularity. So, if I change that, so what essentially will change? Now, the singularity, the point of singular point is at z is equal to 1. If I still apply this formula, then I need to just change this at 1, because now I am evaluating the singularity, evaluating the residue at z equal to 1 point. So, this is 1, this is 1, this has to be 1, and now I am going to evaluate at z equal to 1 point. If I do that, then I will find that it is cos pi, which is minus 1. So, the result will change as minus of 1 by pi. So, at z equal to 0 it is 1 by pi, at z equal to 1 it is a minus 1 over pi. So, we can also generalize these things, because I know where the singularity lies. The singularity lies at all z equal to n point, n is plus minus 1, n is plus minus 1, 2, 3, 4 and so on. So, n here integers 0, plus minus 1, plus minus 2 and so on. So, this is the general singularity I have. I am taking 1 plus minus 1 and plus minus 2, 0 plus minus 1 plus minus 2 and so on. I am taking the general one. So, in that case how to tackle these things? The same thing. So, here the residue will be f z at n point, and the function is g of n divided by h prime of n, which is 1 divided by h prime is pi cos of pi z. Z will be evaluated at pi point at n point. So, now if I put, it will be 1 divided by pi cos of n pi, and we know this cos of n pi, it is minus 1 whole to the power n divided by pi. So, it is the most general form of finding the residue, because there are many residue, infinite number of singular points are there. If I take all point together, then this will be my result. Okay. I hope you understand how this kind of problem will be tackled, and how beautiful this form is, and you can exploit many things with that. So, we will go with few other problems. For example, this one, problem 2, fz is equal to, let us see what problem is in our hand, e to the power z divided by e to the power z minus 1. This is the problem that is in our hand. Again, if you see, I can write this problem as g function of z and h function of z. That is the first thing. Second thing is, I have the singularity at z equal to 0 point. So, though both the functions are analytic, no problem with that, rather there are entire function, because they have the singularity only at z tends to infinity point. So, that is why these functions are, both the functions are entire functions, no problem, absolutely no problem with that. So, the next thing is the singularity. So, z equal to 0 point is the singular point. The singular point. So, that means at this z equal to 0 means at here the function is blowing up, and I should have a singularity only in that point. Also you should note that g of z, which is e to the power of z, is not equal to 0 when z is equal to 0. So, my first condition satisfied, that z of 0 is not equal to 0, and also h of z at z equal to 0, which is e to the power z minus 1 is 0. That is, my second condition is also satisfied. So, that means I can apply my standard whatever the recipe I have, and this recipe suggests it will be the residue of this function at 0 point is nothing but g of 0 divided by h prime of 0. If I apply, then z of 0 is 1, h prime, when I make h prime, then it should be e to the power z only, this one term will vanish, and if I now put, then it will be 1. So, my final result will be 1. So, the residue comes to be 1. Also, you can think this problem in a different way, and this different way is this. I mean, let me just give you the essence of that. So, for example, residue of function sum z0 point, I know it is represented by limit z tends to z0, z minus z0 multiplied by the function fz. This is our standard recipe that I have. If I still apply this here, then still I am getting some result. So, let us find out. Limit, the singular point is at z equal to 0. This is my singular point. So, limit z tends to 0. I multiply z minus 0 to the function, whatever the function is given to me, it is e to the power z divided by e to the power of z minus 1. Now, this limit I need to evaluate, that is all. So, eventually I have z e to the power of z divided by e to the power of z minus 1. Now, this is a 0 by 0 form. When z tends to 0, this term will going to vanish. When z tends to 0, this lower term is also going to vanish. So, in order to evaluate these things, we normally use this L'Hopital rule. So, this L'Hopital rule suggests that I can derive this and then put the limit. I hope all of you are aware of this rule in the 0 by 0 form. So, if I do, then the derivative of these things will be at z e to the power z plus e to the power of z divided by e to the power of z evaluated at z equal to 0. If I do, then I will still get the same result. So, z equal to 0, if you put, this term will going to vanish, e to the power z equal to 0 will be 1, e to the power z it will be 1. So, just 1 in our hand. So, the residue of these things comes out to be 1. Okay. Now, go to the next problem. It is interesting, this form. So, let me do few problems, so that you are familiar with this kind of. So, the next problem which is in our hand is something fz. This is similar, almost similar kind of problem, is sec z, this, simply this. So, now we need to find out the singularity of this function first to evaluate the residue. So, this function, make it simple, cos z. So, where are the z points where we have zeros? Where are the z points? So, the z essentially be 2n plus 1 pi by 2. These are the points where this function is going to vanish. So, if you have remember the function cos function, it will be something like this. So, 0 here in pi by 2, then here it is pi by 2, then pi, and then again 0. So, it is 3 into pi by 2 and so on. So, that means odd for every odd multiply of pi by 2 gives you the 0 of course. Normally, I remember in this way, I do not remember in the general way. Anyway, just to show where the function diverges. So, this is the point where the function should diverge. Now, again we have the same problem in our hand. So, if I try to find out what is the residue of these things, I can consider this function to be as gz divided by hz. Again gz at this point is nothing but 1. So, it will not be 0, and this is 0 because we are doing the singularity, at that point it is singularity. So, the recipe is residue if I am trying to evaluate that point 2n plus 1 pi by 2. This is my point where I am trying to find out the residue, is equal to, if I apply the formula that we derived today, that g of z0 divided by h prime of z0, where h prime z0 is this point. Singularity, I write this singular point as z0 point. So, now if I do, then I find this is 1 and derivative of these things is minus of sine of z evaluated at the point 2n plus 1 pi by 2. So, this quantity 1 divided by minus of sine 2n plus 1 pi by 2. So, I need to find what is the value of sine 2n plus 1 pi by 2 odd of pi by 2. So, we know that odd of pi by 2 is minus 1 to the power n for sine. When sine pi by 2 n equal to 0, then I have 1, when n equal to 1, then sine 3 pi by 2, which is minus 1, and so on. So, this quantity is minus of minus 1 to the power n or minus 1 to the power n plus 1. So, this is the result we have by deriving this particular form. So, here I should stop. So, today we have learned a very interesting thing, that previous class we know there are two recipes that will help you to find out the residue. If a function is given, you first need to find out where is the singularity, and then you calculate accordingly. You can even calculate the residue by expanding the function in the Laurent series, that we will going to use. I will going to use that in the maybe in the next class to show that. Also we have done in the previous class either. Today we have learned that if the function is given in this form, and if hz has a simple pole, then you can also derive the residue in other way, which can be useful in some typical functions. So, we show few problems as an example, and with that I should stop the class here, and in the next class we will start something quite interesting, which is called Cauchy's residue theorem, from where you can calculate the integration and all these things. With this note, let me conclude the class here. See you in the next class, and thanks for your attention.